Alright, let's get started again. So, keep on trucking. We are done, right, with segmentation and paging. So now you actually know how memory access works. Except you don't know anything about caching, but that's okay, because I don't know anything about it. Alright. Miscellaneous intermission, and yeah, that audio is not going to work as well. Oh. So many jokes gone on. Joked. Alright, so we're going to do just like a miscellaneous, like for fun, whatever kind of thing. RDTSC is the read timestamp counter sort of instruction. So like CPU ID, there's no parameters to it. You just execute RDTSC, and what it's going to do is it's going to read from something called the timestamp, 64-bit value, and it's going to place the upper 32 bits in EDX and the lower 32 bits in EAX. So timestamp counter is a 64-bit counter introduced in the Pentium. And so when you restart your computer, it's set to 0. And then every time your clock ticks, it's incremented by 1. So clock ticks refers to like, megahertz, gigahertz, and stuff like that, right? So for your given speed of computer, it'll be incrementing faster or slower relative to real time. And so the point is just, every time your CPU, every time your clock ticks, the RDTSC gets updated. So this can tell you something about the timing of code relative to this processor, and just in general. So, and just as a miscellaneous funny little bit, if you want, there's a flag in CR4 which you can set so that it says, no, only wing 0 may read the timestamp counter. As far as I know, no one does that, but maybe you want to not allow, users code to profile some behavior or something. But there it is. So different families implement the incrementing differently, but that really, most of the stuff is just, once per clock tick. Some of the older things, if you want to ever run RDTSC type checks on older processors, you'll have to go up with that. So there's kind of two different main reasons we're going to see right now. One, using RDTSC to performance test a little bit of code, say about how many CPU cycles does this thing take. Not completely deterministic and stuff like that. Because, the CPU stuff, the CPUs are so complex that, one single instruction is influenced, when that gets done, is influenced by whatever is around. So that's what we're going to do. We're going to do simple lab guesstimate first. This is going to play with, we're going to check the timestamp here, execute some code, check the timestamp there, subtract the difference, and therefore tell approximately how long that code ran for. So guesstimate.c. On your host OS, you're going to want to open up your Visual Studio. You can do it in your guest OS too, and it might yield interesting results, but go with just your regular Visual Studio on your. Going to right-click on Guesstimate and set a start project. Look at it quick. Pretty simple. You declare some local variables, and then you do RDTSC to get the time right now. And then you move over that. So keep in mind that the amount of time it takes includes these two move instructions. But you're moving your upper 32 bits and the lower 32 bits into some local variables. So, you've got a little bit of memory access in there. And then in between there, in reality, it's from this RDTSC to there, so it includes the moves. But we're going to pretend like it only includes this, move 1 to EAX and then CPU. So essentially, we're getting approximately the time that, 3 moves and a CPU ID take to execute. And when we change stuff around, it would be 2 moves plus whatever instruction. Theoretically, the 2 moves is roughly constant, so you don't. Actually, I should remove all the code later. I've never done that. All right, so pretty simple. Set a breakpoint at the very end. Return cascade. Set a breakpoint on the return at the very end, and go to debug and run. Debugging. Run. Great. All right, if we do that, we don't have kernel module windows out in our face. What we'll see is, it'll give us the literal times. It'll say, look, the literal time when you started was this. The literal time when you ended is that. Subtracting them, you have 2 6D X cycles. So it said these 3 moves in a CPU ID took about 2 6D. Now, as I said, this is not entirely deterministic. So, for instance, run it again. Little play button or hit F5 or run with it. Now, this time it took 1 4D for me, right? And so you should see a similar behavior that it's not entirely deterministic in terms of how long it takes. And sometimes you see, I mean, this case, it's like almost half the time. The previous one was, but it's like almost half the time. For the 2. So the point here is, though, this is a generic mechanism by which to see approximately how much time something takes, right? So if you only care about approximate time, you can say, generally speaking, whether something is within. So one thing I already mentioned before was, we said virtualization systems can hook the CPU ID, essentially, right? If you're in a hypervisor, the hardware virtualization can say, look, whenever your guest OS calls CPU ID, we'll give you a chance to lie to the guest OS, right? Say features are or aren't there. Say there is or isn't such physical. So one way to detect virtualization is to use RDTSC and just call like CPU ID a bunch of times under the expectation that CPU ID should take approximately this much time. And if it's taking, some significant amount more after, a million or a billion, right? Then you've got overhead due to some virtualization system trying to hide some CPU ID information. The virtualization system can also hook the RDTSC though. So it can also try to take the RDTSC and subtract some difference if the virtualization system knows what the difference in time is. And so it can lie to you about when you started and lie to you about when you ended so that you get. And there's another way to detect that, but I don't entirely know the details.
Clock cycles.
Well, that's,
should be able to determine how many clock cycles a simple loop takes.
Right. That's why I was saying the issue there, I believe, is with complexities of processor architectures today. It's not really such the case that the only thing going on right now is taking this instruction and doing it. And Jessica, feel free to throw in some comments here. But I don't know if it's going to have a picture here. No, they're not.
Yeah, well, that's
This is the basics and the math as well.
Oh,
So this is what's, generally speaking, going on. You're fetching instructions, and then you're translating them to microcode, and you're dispatching stuff, and all sorts of things. And so, in particular, the thing which I suspect most is there's these decoders and stuff. There's this right there, entry reorder buffer. So the hardware is trying to do a bunch of stuff, not necessarily in order. But at some point, it has to come back and finalize and make sure everything executes in the right order. That's kind of where I suspect the issues come from, is that maybe there were some other instructions which happened to be executing before you, and they're still being processed and stuff in the back. But it turns out you've got to execute those beforehand. I don't know. Maybe it's that. Maybe it's some amount of kernel catching interrupts that's happening behind the scene. But it's definitely not the case that there's so little going on that you can expect. Unless you're really locking down the system and saying no more interrupts, no more kernel switching and stuff like that. If you do that, then you can get to a world where there's a lot more determinism. But even behind the scenes, there's still always this hardware reordering and stuff like that. One of the reasons I threw in RDTSC here was because, yes, you can profile code with it, and it turns out some malware profiles their code. And so it turns out they can detect whether or not you're stepping through them in a debugger, because when you stop at a breakpoint and you look at it and you say, yeah, that takes a lot longer than if you just ran through it, right? So pretty easy, as we'll see. Even if I hit go immediately when I get a breakpoint, still detectable. So let's instead move over to navel gaze. So right-click on navel gaze, set as start a project. After debugging. Yes.
how much malware that checks to see if it's environment and checks to see if it's bugs technique?
I can't say, using this specific technique, but generally speaking, there will be, packers which include a bunch of different virtualization and anti-debug, anti-VM, etc. And so the point is they can just keep loading those up, and then anytime you pack something with it, it's just built into the unpacking piece. So similarly, anyone could go ahead and, typically it's just going to be built in. But maybe other people like they. So we're on navel gaze. We've set that as, yeah, let's not even look at the code right now. Well, no, let's open up the code and not like dig into it. We got a malicious function, we got a benign function. It has to do with the difference. See that, main executes some function 1, some function 2, some function 3, and then it does a check on something, upper diff, lower diff, and then it maybe executes malicious, it maybe executes benign. We don't know what this code is actually going to do at this point. So go ahead and set a breakpoint at the very end, whatever it is, return tactless. Set a breakpoint at the return at the very end of main, navel gaze, and then go ahead to run, start debugging. Right, so we do that, we pull up the window which just executed, and what do we see? La-di-da-di-dee. La-di-da-di-da. Right, got you at hacks, didn't you? Well, that is not what it's supposed to do. Which is interesting. It's supposed to say it's, wait, is it innocent? Yeah, okay, I did it wrong. Here's how we're supposed to do it. We set a breakpoint on some function 2. That was fail buggery on my part. This happens when you rush. All right, so we set a breakpoint on some function 2. Maybe for whatever reason we think that's suspicious. Right, so we go to debug. We go debug, start debugging. We set the thing on some function 2, and we click on it and we go to definition, and we say, oh, okay, well, all that does is return alfalfa. So let's not care about that. Let's just go ahead and run the rest of the program. Then we get the output and we see, la-di-da-di-dee. See, I knew it should have rhymed with. Right, so when we set that breakpoint, this thing says, I'm innocent. It has some behavior. And when we don't set that breakpoint, right, don't set that breakpoint, run it again, and this time, we've got. Right, so the point here is different behavior based on whether or not there's a human sitting there at the debugger. And to what degree is that possible? Well, possible to the degree that go back and set, a breakpoint on some function 2. Keep in mind the F5 command is the go command. So we're going to hit F5 to run it, and then the second we see it stop to breakpoint, hit F5 again. F5, F5. Particularly fast. Still innocent as can be, right? The point is, all it's doing is in some function 1 and some function 2, it's using RDTSC to start timer, stop timer. And it goes and checks the difference. This is nice and easy. When you are looking at, a couple megabyte big piece of malware, you don't know where the timer starts, you don't know where the timer ends, but you certainly should be suspicious if you ever come upon an RDTSC. It means you see RDTSC in something that you believe you're analyzing malware, should be suspicious that it's using an anti-debug check where if at some point you set a breakpoint, that's going to influence its timing, increase the amount of time, and somewhere it's going to have a heuristic where it says, I should take approximately 5,000 CPU cycles, 10,000. When you add in a breakpoint, you kick it up to millions and very quickly. Run at 1 gigahertz, that's 1 billion cycles per second. Run at 1 gigahertz, set the, wait for a second at a breakpoint. You've just kicked it from, 500,000 to up to 1. There's a little in the malware analyst's bone. You've already probably. So all the aspiring malware analysts, now you know RDTSC was probably anti-debug. Keep your eye out. What's the other anti-debug? Saw some in the intro class, I know. So, that's all I wanted to say about RDTSC, fun little diversion. Throw in a command that you may see. Yes. Yes, that's what I was saying. You can intercept the RDTSC and like subtract the difference if you think someone's doing timing, or if you just want your timing to look more normal. All right, so pop quiz, hotshot. You've got malware that's altering its behavior in response to your breakpoints. What do you do? What do you do?
Shoot hostage.
Hostage.
Terrorists win.
That's right. Stop letting the terrorists win. Anyone else? I don't know what the answer is. I just threw this.
Using just change read the edit in a debugger.
Yeah, that's a good one, right? So you go, if you can find where they're checking the comparison, right? If they're doing the comparison of their timing, if you, then yeah, just modify, let it continue on. Still need to go find that. So if it's like some huge login program, you're looking for a compare, you're looking for an RDTSC, and yes, maybe you can have a static analyzer look for all RDTSCs, then you need to like go find where that compare is, right? You need to track that memory where they store the values. Maybe a local variable, maybe a global variable.
I was going to say, but also use their own tricks against them and insert a jump right before.
Yes, I was going to say, wouldn't it be better to do like jump over RDTSC, but yes, first
Yeah,
it's still
depends on
there.
the comparison.
Right, exactly. If 0 passes, then yeah, jump over RDTSC. Alrighty. Keep that in mind. Such a good image. All right, on to interrupts. We definitely got to get through this today. We will get through this. It's only a question of how much time we're going to have to pass this. We want to at least make sure we hit, hardware debugging, software debugging, stuff like that. Once we get through interrupts, software debugging makes a lot more sense. All right, interrupts and exceptions indicate that a condition exists somewhere on the system that, hey, stop what you're doing, pay attention to me now. Okay? That can be a case of, hey, you got a network packet, pay attention to me, pull it off of my buffer. I've only got so much space to buffer these packets, OS. Come get it off the NIC card, right? Keyboard, keystroke, yes, you just got a mouse movement, you got a keystroke. CPU, pay attention to me, update the mouse on screen, update the keyboard, right? That sort of thing. And it could also be error conditions, right? Page fault handler, we saw already, interrupt 14. Hey, hardware says you're trying to access memory which isn't, there is no valid virtual to physical address, or you're trying to write to what should only be read from, all that good stuff. So stop what you're doing, pay attention to me, let's vector somewhere that handles this particular. All right, so there's two sources of interrupts. There's external, the hardware that I just talked about, NICs, Ethernet, NICs, keyboards, mice, hard drives, right? Hard drive says, hey, you asked me for this thing, done. Got the data ready for you now. Other one is software-generated interrupts. You'll see an interrupt instruction eventually, which you can call manually. It says, I want to cause an interrupt, which vectors to something in the scripture table. All right, so difference between interrupt and exception is basically, typically one considers exceptions to be error conditions. So there's something erroneous going on. Interrupts is just saying, hey, something happened. Someone's talking about an exception, that's bad. Something's happening about an interrupt, that's ambiguous. Interrupt can just mean something happened, pay attention. An exception typically means something bad happened. Of those bad things that happen, there's kind of three categories. There's fault, trap, and abort. So a fault is recoverable. So this is something bad happened, but you can recover it. You can. Well, I don't know which is which, but I'm pretty sure the page fault handler handles page faults. Page faults are false. So fault recoverable. It pushes the EIP of the faulting instruction. So this is kind of a double helpful thing for page fault at least, right? We said when a page fault occurs, CR2 gets updated to the address, the EIP of whoever was trying to access memory that it can't access. But just generally speaking, for all faults, when it happens, it pushes the EIP of the address which was trying to, write memory to, memory address 0. So when a fault occurs, you can expect on your stack there will be a nice, helpful little EIP that happened. And since this may or may not be recoverable, it at least has the possibility of being recoverable, you may be able to return from that interrupt, return from that exception back to that EIP after you, for instance, silently updated your page tables. Go for it, return back to that EIP, and let it continue on, and it's none the wiser. Trap is also potentially recoverable. The only difference between fault and trap is EIP in a trap is the instruction after the instruction that caused it. Some cases why you would want that to be the case later, but it basically is for cases where you had a trap, you move one instruction past because when you return, you don't necessarily want to return to the instruction that caused it, because maybe if you return to the instruction that caused it, it's going to cause it immediately once again. Maybe you just want to move one instruction forward, get the fault, fix whatever you need to fix, and then continue at the next instruction. So different cases for when you would want to do this. Finally, abort is unrecoverable. The EIP may or may not be able to be saved. You shouldn't expect it'll be saved. And really, it's just sort of an error condition where you can't deal with it. Got to crash now. Whether you have to crash the OS or whether you have to crash the program first. But certainly, we talked about before, you may be able to have the OS pass down hey, user space program, did you mean to divide by 0? And if so, can you fix it yourself? Right? So user space can register that it can handle certain exceptions, but in the abort case, the OS is never going to pass chances an error so serious, I know there's nothing you can do about it. Okay. All right, so that you can remember how this all works, you take nothing from this class. I should be able to ask you in 6 months or when the rootkit class comes out, where does a fault point? Fault, EIP points at the faulting instruction. EIP says, this is the instruction which caused the fault. And so, this is all your fault! Exactly. I agree with you. It's all good, I'm a quarter German. I share the shame. Trap. EIP points at instruction after the trapping instruction, right? EIP, it's a trap. You all know that. Can we all? It's a trap.
It's a trap.
Thank you. Excellent. Saved for posterity. Good job, man. Doesn't matter. You don't need the group to do it. All right, and abort. Possibly unrecoverable. So again, if you take nothing else from this class, you should at least be able to remember these pictures so that later on, you can remember it's a trap, but you just need to think, where was it? Right? Was EIP at or after the instruction? No. Fault points at, EIP points at the faulty. Abort is unrecoverable. I don't know off the top of my head. I don't remember. I'm guessing double fault. So I don't know. Actually, there should be a picture in here later where we talk about some Intel system-defined interrupts. There's system-defined interrupts, and then there's use. And there'll be a couple of those that'll be listed. Find out when we get there.
So I got one question about this.
Yep.
You're saving the IP. Are you?
Hardware is saving the EIP, first of all.
I'm sorry, what?
First of all, hardware is saving the EIP. So hardware exception, fault, instruction, whatever happens, hardware says, I will put this onto a stack.
Okay, yeah, that's what I was wondering.
Okay, that's wondering.
That's the main thing.
Yep, that's all that happens. It's again a case where hardware saw that So I said there's software interrupts and there's hardware interrupts. So there's these things called advanced programmable interrupt controller. There's actually another little chip out there which accepts these interrupts in from hardware devices and then gives them. Sometimes they will be masked such that these are not allowed to be delivered to right now because or you can say that this one's higher priority than that one. Anyways, there's other interrupt controlling hardware out there. But the point is, when these, especially when these hardware interrupts occur, there are some interrupts where when a hardware interrupt version of it occurs, it pushes an error code, for instance, in addition to this EIP, but still it's always the hardware which is pushing EIP of whatever it found. Maybe it has an error code, maybe it doesn't. It's definitely the hardware's job to push that onto the stack, wherever the stack is. Right, so at some point, this is referring back to my previous slides, which I didn't actually say, but the point is, when I was talking about the interrupts, I said the system must be suspended, right? You must handle this interrupt right now, right? It's something that needs to be handled. Maybe you want to just handle it to the minimum degree and then like just resume the system and copy whatever data from the packet off to a buffer in main memory, and then you'll come back to it later. That's handling it, but the point is you got to handle it now, and so whatever you're doing right now, it gets interrupted. So you need to know how to get back to whatever you were doing at the time that you got interrupted. So there's going to have to be some save state. There are two calls, right? Call, you need to know how to get back to the next instruction. So it's automatically EIP onto the stack. Same kind of thing, what is necessary in order to get you back to where you were. It's going to be things like EIP, your CS register. You should see that in this next picture, yes. Right, and then this is where I actually say it's the hardware itself which saves this information, which is. All right, so a couple different things. There's stack usage with no privilege level change. So in the simple case where you're running in ring 0, you get an interrupt, and it's handled in ring 0, you have to save less information. So specifically, if your ESP was here, then the things that will be pushed on the stack automatically by the hardware are E flags, CS, EIP, and maybe an error code if it takes an error code. So you as the OS, when you handle that interrupt, you need to know, is this an error code pushing interrupt or not, because that modifies what you're going to read off the stack, right? If it doesn't push an error code and you try to read an error code, you're going to mess up. Anyways, that's the minimal information. You can see that the CS plus EIP, well, that looks a lot like a logical address. You've got a logical address on your stack telling you where to get back to, because you can potentially have, inter-segment interrupts and stuff like that, depending on how the interrupt table is set up. Next, there is stack usage when you have a privilege level change. So that means I'm in ring 3, happily running along, network packet comes in, interrupt happens. This interrupt happens to vector to ring 0, because it turns out there's a logical address in the interrupt table as well. So I can be in ring 3, and then I hit an interrupt, and it turns out to vector to ring 0. That's a privilege level change sort of thing. That's this bottom case. And in that case, there's this interrupted procedures stack, but we see that actually the data gets pushed over onto this other handler stack. Okay. So the data, when you're having a privilege transfer, if you're in ring 3 and you get an interrupt, the data is not stored into your ring 3 stack. The hardware goes over and it finds some other stack, which is the handler stack, and we'll see how you get that in a second. It needs to look up, who's going to handle this, where's their stack, I'm going to push it there. I'm not going to, push it into ring 3 stuff, because the handler is actually ring 0. So let's put it on his stack. Let's not be data for ring 0 to ring. So on the handler stack goes SS, ESP, E flag, CS, EIP. Now we got two logical addresses. SS, ESP, which we said was all of the data access, is implicitly always SS relative, right? SS, ESP, that's your sort of data segment, right? And we saw that it goes 0 to FFF. So now, because we're transferring between different rings, we got to store, the full out, ring 3 code had this stack, had this, segment, stack segment plus its offset into its stack right now is ESP. And ring 3 code had this code segment, and the offset into its code was this EIP. So store those later. And E flags again is just stored because you've got some state in the flags which you maybe want to restore. Again, you may or may not have an error. All right, so this is what gets pushed onto the stack when you have an interrupt. So conceptually, we know, like a call instruction, there's going to be an interrupt return, which says, when I'm done with the interrupt, call an interrupt return. It expects this data on the stack just like a return expects an EIP on the stack. Got the wrong stuff? Too bad. It's getting stuck into these registers one way or the other. Same thing as buffer overflow. Got the wrong stuff, top of the stack, and you hit a return instruction. Doesn't care. Puts it into the EIP register, right? Same thing here. Doesn't care. Whatever's on the top of the stack at the time that you issue the interrupt return, it's going to just go back into these registers. So like I said before, sort of, when I was talking about like how does kernel space jump into user space, like in the very first user space process and stuff like that, I suggested that maybe it uses something like this, right? You can set up a fake SS, ESP, CS, EIP, right? Just set that to whatever you want to start this new process, and then the kernel just interrupt returns, and it goes back to its first instruction of this new. So that's one of those. This is one of those ways that you can set CS. I said before, you may not just do move whatever you want to CS. There's only certain ways to do set CS. This is one of those ways. One way is to jump through a call gate. This is another way to turn back from. Also to cause it. All right, so you couldn't find your handlers stack with both hands. So this was a good question asked by my wife, which I didn't really ever dig down into the fact. And actually, I had not paid attention to the details of this slide. And I just thought, oh yeah, well, it just sticks it wherever ESP is right now. But no, as this slide says, handler stack is different when you're going like user space. So how does the hardware know where the handler stack is? Because it's not an ESP, right? ESP is whatever user space is. How does it find the hardware? How does the hardware find the correct place to push these values onto the stack? All right, so the answer is there's these things called task state segments, which are meant to hold a bunch of state information about. Intel put them in there to try to help OSs with like switching between this task to this task. It holds like a bunch of register information. Turns out people don't use it really because I think it had some performance issues and things like that. So, but still you're required to use it to this minimal degree, like with segmentation. You must at least use segmentation to set up all of memory segments. You must at least use this task state segment to set up an interrupt handler stack. None of the rest of it actually matters. I really dug down into the manual. It says it really is, the hardware really is only looking at this one field, task state segment. So, like this says, you can read volume 2A, section 6 to find out what Xeno doesn't want you to know about task state segments. But the point is, as the slide is saying, you must at least have some sort of this data structure set up. We'll see the data structure on the next slide. Data structure must be set up because the hardware is going to be consulting this data structure. How does the hardware find the data structure? Task register. So like the GDT, how does the hardware find the GDT? GDT register. Does the hardware find the LDT? LDT register. How does the hardware find the task state segment data structure? Task register. Task register is yet another segment selector. 16 bits, and it says, hey, somewhere in the GDT, there's a memory segment of type TSS, which in reality is describing a memory segment which should have this form, right? So somewhere in the GDT, there's a pointer to, a base plus limit and, a DPL of whatever, everything else. But really, it's just describing memory which should be used like this by the hardware, by the software if it wants to use it. And the key point here is, as we will see in a little bit when we run a lab, we'll see that most of this is all junk on Windows. But this right here, ESP0 and SS0, that is definitely valid. And that is what the hardware uses. It transitions when it gets an interrupt in user space, goes out, looks at the task register. Task register as a segment selector. Goes to the GDT at the selected segment. At that selected segment, there is a base and limit. That base and the limit covers the start of that and the limit wherever the top of that is. Turns out there's some stuff that is variable size at the top. And so the hardware knows, okay, that's how I can find one of those data structures. And I just need to go offset 4 into this to get the ESP of the handler for interrupts and the SS for the handler of interrupts. That specifies a logical address again for where the hardware should dump that stuff onto the stack. Yes.
So is it one TSS per interrupt? Or is it,
It's
there's
a global
one
sort
for
of thing.
user space and one user space stack and the other for stack?
It's actually the case that what I found out when there's one per ring, but not per ring. So this is what I found out when I dug into it. This right here, the point of this ESP0 is it's saying if your interrupt, if there's a privilege level transfer, right? So I'm going from ring 3 to something else. And if I'm going 3 to 3, don't care. Just put it on the same stack. That's what that first picture is. 3 to 3, 0 to 0, don't care. Just dump it wherever ESP is right now. 3 to 0, 1 to 0, 2 to 0, those are all privilege level changes, right? And so the point is right here, ESP0 is the stack logical address for ring 0. If you're going to ring 0, go grab that stack address. If you're going to ring 1, the hardware goes and grabs this, ESP1, SS1. You're going to ring 2, so you could go 3 to 2, for instance, right? And then you would have the hardware going out and grabbing ESP2. No one uses that.
I see
Did you see 2 what?
TSS entries.
You did. You saw multiple TSS entries, and I don't actually know what a bunch of those are. But I know the core one. You can find the core one, which is used by interrupts, by looking at the task register, right? So you go to whatever TR is, right? Task register will say, here's the thing which is currently active. And whenever I can look at it, it's pointing at this. I suspect some of them are maybe for early in system boot, but then I would expect 16-bit ones. So I'm not going to even speculate. Don't know, don't care. Never affected me in any. But I'd still be interested in knowing what they're for. Don't completely not care, but I don't care to the degree that I'm not going to go look it up. So you go look it up for me, and then I put your name in the slide saying you're awesome. Deal? All right, let's do WinDebug, and let's take a quick gander at the old TSS. And I'm totally into that part of the day where my eyes are now. I'm sure you as well. All right. Does everyone have their WinDebug from before still up? I think we're not going to care that we're in non-PAE mode. It really shouldn't matter. Everyone's got that up? Everyone on the... people on the phone, please shout out if you've got the debugger already up. All right. Here's what we're going to do. First of all, we're going to find the task register in the registers window off to the side. There it is. It's at the bottom. TR 28. 16 bits, that's a segment selector, right? So what did we learn about segment selectors? How am I going to find whether this is GDT or LDT? How am I going to find what index this is? Right, so first, someone tell me GDT or LDT. Do we even have to do that? Yes, there is no LDT. GDT. All right, so what index is this? How do you split that index bits out of a segment selector? Yep, you mask off the bottom 3. So if you mask off the bottom 3, what is this number? This 28 shifted right essentially 3 bits. Probably just like write it out. This. What is 2? 0, 0, 1, 0. What is 8? 1, 0, 0, 0, but I don't care about those last 3 bits. What is 1, 0, 1? That is 5. Yes. Index 5 in the GDT. My task register is saying if I go to index 5 in the GDT, I should find a task state segment. Right? So how can we do that? Well, first of all, let's for instance do bang descriptor. And let's say, well, let's just go ahead and do GDT 5. Okay, so bang descriptor space, capital GDT space 5. Do it. dot load space tote mode like this. Dot load tote mode. You should still have it in your plugins folder. So if you don't have it, you dot load, and then you should be able to. Question? No? You got it? All right, good. So do Bang descriptor space capital GDT space.
Oh, it's just the one starting back. Good. Nothing. Nothing easy.
Let me see here. No. All right, so we can see that it does tell us that the type is of type 32-bit TSS busy, right? So now let's look at this with this extra little command that I threw in here. Bang descriptor, TSS32, and it turns out, I think, correct, yes, I didn't make this all convenient-like, so you can't just specify that 5. You need to actually specify the base address that you want to interpret as a TSS thing. So the base address, according to this GDT thing, is 8004200 on mine. So I'm going to do bang descriptor TSS32 space, and then the base address that I just got from that GDT command.
Incredibly dense, I'm sure. But, how many shifted left 3 bits 3 because it's 1 or 0 to start with? And you shifted left 3 to get
It's not 111 101 000. So 28, right?
Yeah.
So it's 2, which is 0010, 8, 1000. You're thinking,
Oh, that's hex 28.
Hex
Yeah, I was in decimal. Sorry.
yeah, you can see all of these register values over here. But yes, just looking at that, you would know in isolation.
Looking towards either above or below.
All right, so bang descriptor space TSS32 space the base address, and what do you get? All right, you get a whole bunch of nothing, but what I'm claiming is real is ESP0, SS0. Claiming this is the logical address for the base of the stack when an interrupt occurs. So when an interrupt occurs, hardware goes out, checks this, changes SS to segment selector 10, right? And 10 is, again, it's a segment selector, so you got to, shift it down 3 bits, right? 10 is 0001, 0000, right? So move 3 bits and you get 2. So we know from before, GDT entry of 2, don't remember from before, GDT entry of 2 is 0 to FFF, EPL 0, so it's ring 0, all of memory, and it's a data segment. So the SS of segment selector 10 is that all of memory kernel data segment. Right? So it's moving to the all of kernel data segment, and then it's moving to offset 80550. It's just the base of the stack when an interrupt occurs, and that's where in kernel space you should see the stuff. So you should expect that when you're in kernel space, immediately after an interrupt occurs, your stack is like 8055 plus however much stuff just got pushed onto the stack by the hardware automatically. That's how the hardware finds where it's going to push the stuff. Alrighty. So that's all we really care about TSS. We only care about it in order to sanity check that that is how the hardware is figuring out where the stacks, where to dump stuff on the stack. All right, so now onto the actual interrupt descriptor table. So it's an array of up to 256 8-byte descriptors. So like the GDT, we got 8-byte descriptors, 64-bit things. You're going to see they look very much like GDT as well. They look much more like call gate entries. In fact, they look almost exactly like call gate entries, but we covered call gates so quickly that I wouldn't expect you to remember. So 0 through 31 are actually reserved for architecture-specific things. This is where Intel says, look, if you're handling interrupt 14, that's always page fault. Treat it as such. If you're handling interrupt 0, that's always a divide by 0 exception. Treat it as such. So 031 specified, although some of them are even just Intel reserved in 32 to 255 are all user defined, so put whatever you want there. As long as, you know, for instance, your hardware knows to call this interrupt number if you have a network packet. That just so if you're going to ask me how I know that, how you tell the hardware, or whether you tell the hardware, or whether, you know, there's just conventions, I don't know. All I know is I go into the IDT, I look at it, and if I see a symbol name that looks like it's something network, then I know on this system the network interrupts. Actually, as we'll see, as long as we keep booking it, as we'll see when we get to the keystroke logger example, the keystroke interrupt can be in different things in different systems, actually. But when I had to modify that from some systems use, or inside of a virtualization system, it uses a different keystroke interrupt than the original code, because it can actually move around a bit. So you can think of the IDT as being an array of function pointers, and I put this in here, but in reality, it is important to think of it more like an array of logical addresses or pointers. So if you are function pointers, but they're not just function pointers in the sense that normal function pointers, like, you know, 32-bit offset with, you know, unknown implied segment selectors, right, which hardware just uses automatically. It's an explicit logical address where the interrupt descriptor table has segment selector plus 32-bit offset. But I guess I'm not ready to show you that yet. So a couple more slides. First, I want to talk about the reserved or predefined interrupts. So there's different mnemonics, and the mnemonics only matter if you're like looking through the instruction set thing. It will say like, look, if you try to do this in ring 3, but it's actually privileged, it will throw general protection fault. Divide by 0 is conveniently interrupt 0, and this is of type fault. And so in each of these, this column, right, it tells you, is it fault, is it trap, or, you know, is it interrupt, and is it abort. So, oh yes, I win. Double faults, despite being called a fault, is an abort. So, good. Double fault is like when you get an interrupt when you're already inside processing an interrupt, and you've like said, "For interrupts, please," but you still get an interrupt. That'll happen if, for instance, you call an interrupt instruction inside of your interrupt handler. So, yeah, that shouldn't happen. You should handle one interrupt, handle it to completion, and then, you know, return back and let whatever happens next. But if for whatever reason, for instance, if you're not properly like masking off and stopping other interrupts from occurring while your interrupt is being processed, like there is a way that you can say like, no more interrupts, please. If you don't say that, and you get another interrupt, you'll get a double fault. So, bane of the OS. That's pretty simple. All right, ones we really care about for later. DB, calling it reserved interrupt 1. I have no idea why they do this and why they say it's for Intel use only. That's the debug interrupt. This turns out to happen if you have used hardware interrupts. Right, so not software interrupts, or sorry, you're using hardware breakpoints. So there's two types of breakpoints which a debugger will generally export to you. It'll say, if you just ask for a regular breakpoint, that's going to be a software breakpoint, and that is interrupt 3. Right here, BP breakpoint, and it is of type trap. So where's the IP going to point after an interrupt 3?
Instruction after IP?
Instruction after IP. Right, what about breakpoint 1, hardware breakpoint? Either, right? Maybe it'll point at EIP, maybe it'll point after. It depends on the type of hardware interrupt, hardware breakpoint which you set, and you'll see that later. So interrupt 1 and interrupt 3 are definitely things you want to understand, and we will get into later for understanding how debuggers actually work. If you're a debugger writer, so we're going to get into it to the point where it's like if you wanted to write a basic debugger, you probably could almost do that, most of the way do that. Certainly you can make it so that if you want to write something which screws with interrupts, like your, you know, malware, and you want to not allow the OS to catch any hardware breakpoints or software breakpoints to debug you, you can certainly do that by hooking these two, or going to the existing handler and hooking it there, or doing some other stuff. So don't care about other stuff like overflow, bound, invalid. Yeah, don't really care about the rest of that. General protection fault, this is sort of like the catch-all, like, whenever you're doing something that's just wrong, in the manual it'll say, if you do that, then that's not general protection. But it is still a fault, and there is still the possibility that you could recover from it. It's not like a straight up. Here's another one, machine check abort. I'm not sure exactly when that happens, but it is another one like general protection where if you dig down into the details of the instructions, it'll be basically saying, look, if you really do the wrong thing with this instruction, or if some weird conditions happen, then you can't deal with it. But the only other thing I wanted to talk about here is interrupt 14, page fault, if, oh good, yeah, so it does have an error code as I thought would be required. When a page fault occurs, right, it's occurring because of the hardware. You're not like going to automatically, you're not going to say like, hey, interrupt 14. No, the hardware is going to be walking the page tables. Oh, present not set. Bam, page fault. And it puts an error code. So going back to this right here, for those interrupts where it says, yes, I give an error code, as the OS, when you're handling this, you need to expect this on your stack. And if it says it gives an error code, you better expect an error code on the stack, and you better read it. And, maybe, I presume the page fault error code will tell you something like, hey, this was, user code trying to access super. The handler figure out what's going on. If there's no error code, don't read it, because otherwise, yeah. So, anyways, this is where, for instance, error codes can only actually occur in response to hardware interrupts. So you can't like define an interrupt and say, yeah, I want my interrupts that are software interrupts to have error codes. Error codes are only ever pushed by hardware. Only for whatever's in this table that says, yes, I give an error. What?
Right.
Well, but you don't really need to define them in the sense of, the error codes, you can define them in the sense of, how would you? Well, as we'll see in a little bit, you could, for instance, if you wanted to do a software interrupt and you wanted to kind of like pass something about, hey, what's going on, it turns out that most of the registers are not overwritten when you just do a software interrupt. So you could, and that's, actually that's exactly the point with those int2e and int80 that I was talking about, calls, right? A bunch of the registers are not overwritten. If you want to pass information by way of an interrupt, go ahead and, like the syscalls do, set EAX to the index in the system call table that you want to call, right? And set EBX to, some. Yeah, that's why error codes really only pertain to hardware is dumping some extra information onto the stack, but it's not always. That's all I really want to talk about. Page fault is key. General protection is, catch-all. And then breakpoint is a software interrupt, or software breakpoint in a debugger uses interrupt 3, and a hardware breakpoint using the hardware uses things. And the other thing I wanted to say is the seg fault is a lie. When you hear, segmentation fault in Unix type systems, right? Knowing what you know now, you would think, oh, well, you're trying to access outside of the segmentation bounds, right? But also knowing what you know now, that segmentation covers 0 to FFFFFF, right? You're never accessing outside of the segment bounds. Where is the seg fault coming from? It's actually this sig-segv, and yes, it's conceptually meant to deal with things like segmentation errors. But because no one uses it, in reality, it's more like a catch-all. And behind the scenes, it's probably something more like a general protection fault or something like a page fault. And so sig-segv is actually just a signal that kernel space sends down to user space, and user space may or may not. So just like Windows has structured exception handling and also another type of exception handling where kernel can say, look, something bad just happened with you process. Here's what bad happened. Here's what happened. Can you do anything about that? Do you have any handlers registered that? Unix does that. Windows does that. In Windows' case, it's called, signaling. But you can see how you can register to catch signals like sig-seg, like a whole big old list of here are the signals you can catch. I like Control-C is one of the signals, for instance. That's the name. If you've ever seen those applications where you hit Control-C and it says, aha, no. Like, remember the bomb lab in the intro class? If you hit Control-C, it prints out, so you thought you could stop me with Control-C, right? And you hit it again, it says, okay. Right, so that was just a case where it's catching a signal, right? Okay. So go for looking that up at your leisure. So 5-minute break, and when we come back, we're going to talk about the actual instructions, and then we're going to do a lab and look at user space to kernel space. If you execute a software interrupt, these are all software interrupt and interrupt return instructions. If you execute a software interrupt, here's what happens. Here's what the state of the system was in user space. That's try to run, try to hide. And when you get into kernel space, you break on through to the other side. It'll show you all the registers. So 5-minute break.